All right, so first of all, what is this? Well, this kind of looks like the following. Here you go, psi A of x, and then this is psi B of x. And so what you recognize this as is what we call the overlap of A and B. Okay, so what Griffiths points out is that if you're doing this experiment, and if you have two electrons that are identical, if you have electrons and they are identical, and you want to do this problem, find out the expectation value for these two, the expectation value between the difference of these two particles, and one is in Boston and the other is in Chicago. All right, then how big is the overlap of the two wave functions?
Very big.
I mean, one's in Boston and one's in Chicago, right? So this term is extremely small. So that this effect isn't for, and so in other words, all electrons and everything are essentially identical. So we should have this huge overlapping wave function. But the reality is spatially separated electrons that are spatially separated by a big distance, their wave functions indeed are pretty small to begin with. And so this effect doesn't show up. So if you're doing this experiment very far apart, in other words, what we're really getting towards like entangled. How entangled are these electron wave functions? Well, if one of the experiments is in Boston and the other is in Chicago, they're not very entangled to begin with.
Right. More entangled with Boston or Providence.
Yeah, even that's pretty far though.
It's still more than Boston and Chicago.
Okay. But that's the idea, really, that term, okay? Okay. So what does this term tell you about the electrons and how close they are together? It tells you the following. It tells you that if you have, so here we go, if these are classical, so this is the expectation of x1 minus x2 of quantity squared. This is plus, and then this is. So if our classical result is right here, that's how far apart they are classically. What does it say over here about if they're bosons? Are they further apart or are they closer together?
Bosons are closer.
The bosons are closer. So here we go, the bosons. All right, and what if they're fermions?
They're further apart.
They're further apart. Okay, so what it tells us is, depending on whether they're fermions or bosons, even though we didn't include any type of repulsive force over here, just by very nature of this new symmetric and antisymmetric wave functions, what do we get? We get some type of like quantum mechanical exchange force. All right, and that's the whole point of this section, is the exchange force. That for bosons or symmetric wave functions, it looks like they're closer together, and for fermions, they're further apart. All right, so we're now going to get to a very important thing. This is the key result that you need to know. And we will be almost done. I want to just do Fermi energy, but I want to get to Hund's rule right now. Okay, so let's do this. So let's take a proton and a proton. So let's take a proton and a proton, and ignore the protons for a minute. And let's take two electrons. So this is going to be H2 molecule. Right. Now, electrons, so let's look at the electrons. So where do the electrons go? Electrons go. Right, now, the electrons, let's ignore everything else. All right, if they're electrons, they're fermions, right? So they should have an antisymmetric wave function. So should they be closer apart or further apart?
Further apart.
They should be further apart. So if this is all we had, we would have one electron here and then one electron over here. And would that ever form a molecule?
They can't share the electrons.
Yeah, there's no sharing of it, right? But if the electrons were bosons, then you'd have a proton here and a proton here, and what does it say about the separation between them? It's smaller, so it'd be here. You have electron 1 and electron 2. All right? And so, if I have an H2 molecule, it seems like counter that the fermions are saying that they're further apart, right? Than the boson wave function. So the answer would be, you go, that's kind of funny. It looks like electrons should be in a boson wave function or a symmetric wave function, right? For this molecule to exist, all right? But we have ignored a super important thing, and that's electron spin. All right? And so what we have ignored electron spin. All right? And so here's how it goes. It has to be like this. The psi total for 2 electrons has to equal psi the space for 2 electrons. Right? So that's the spatial part, but what else does it have to include? It has to include the spin. All right? So let me write it like this. It has to include the spin. Total spin for 2 electrons. Okay? Now, electrons are fermions, right? Okay, so what should this whole wave function be? Should this be a psi plus or should it be a psi minus? It should be a psi minus, right? Because that has to be. Okay, so check this out. What if I made this, the spatial part, psi plus? So I made it psi A of R1, psi B of R2, plus psi A of R2, psi B of R1. All right, this was formerly my psi plus for bosons. All right, but stop calling it bosons now and just say it's psi plus. It's symmetric. All right. Now, I have to multiply this times the psi total for 2 spins. Do you guys remember for 2 spins, you could have you could have the following. You could have an up, or you could have 1 over radical 2, an up, down, plus down, up, or you could have a down, down. Okay? This was for 1, 0, minus 1. Or the other wave function you could have with a 0, 0, and that was 1 over radical 2, and parentheses. And this was an up, down, minus, down, up. Right? I'm almost done. Right? And so what type of, is this symmetric or is this anti-symmetric, these 3? Those are symmetric. What about this one? This is anti-symmetric. So what if I put this all up here, I did the 0, 0. This would be a symmetric times an anti-symmetric. And that will give me an anti-symmetric. And then this, what is for the spatial part of the electrons, what does this tell me about the electrons now? What case are they? They're closer or they're further apart? They're closer together. And then what does it tell me about the spins? The total spin of the system. They're anti-aligned. One's up, one's down. All right?
And there's no other way to go.
So that's so right, that we just threw it back in. All right.
If you ignore the spin, you would be wrong. Therefore, spin must be wrong.
So we've got to have the spin in there, yeah. All right, guys. All right, so I guess we'll finish this up on Thursday. All right. And then we will get done, because I'm going to go over Hund's rule in general, because it gets a little bit tricky, and then we're just going to get the Fermi energy levels, and then that's it. And then we'll start on chapter 6, which is perturbation theory. All right? So continue to work through those homework problems, all right? You should be able to do a little bit more of them.
I'm still thinking about doing that, extra class.
Yeah, we're gonna have to do extra classes, yeah. Let me think about that starting next week, okay?